Hello friends, I welcome you in lecture number 14 on group theory. In this lecture we are going to discuss one special term known as subgroup of a group. So first we will define what is meaning of subgroup, and then we will see how to show that given subset of a group is a subgroup of a given group. So suppose G is a group under the binary operation say star, then a subset H of a G is called a subgroup of G if H itself is a group under the same binary operation of G. So if a subset H of a group G is also a group under the same operation of group G, then we say that subset H is a subgroup of group G. So whenever we are given any subset of a group G, then that subset is going to be a subgroup if it satisfies the conditions for set to be a group. Now to check whether H is a subgroup of G or not, we don't have to check all the properties of a group. If we can show that these three conditions are satisfied, then we can say that a subset H of a group G is a subgroup of G. So first condition is H must contain the identity of group G, that is E belongs to H, where E is the identity of a group G. Now we are considering the same binary operation which is given for group G. So our set H must be closed under the binary operation star. That means if we take any two elements in H, then A star B must be in H. And third requirement is if we take any element in H, then its inverse must be in H. So if these three conditions are satisfied, then we can say that a subset H of a group G is a subgroup of G. So some authors consider these three conditions as a definition of subgroup also. So here we have written both the definitions. Let H be a subset of a group G with star, then H is called a subgroup of G if H itself is a group under the binary operation star of G. And another equivalent definition is, suppose H is a subset of a group G with binary operation star, then H is called a subgroup of G if it satisfies the following three conditions. So these are the conditions which I just discussed. First requirement is H must contain identity of group G. Second requirement is if we take any two elements in H, then A star B must be in H. So this is the closure property for group. So this property says that H must be closed under the binary operation star. And third property is if A is any element in H, then its inverse A inverse must be in H. So we can say that H is closed under inverses. So we will remember both the definitions. And now if we don't want to go using definition, then we have simple subgroup test also. This theorem provides another test to check whether a subset of a group G is a subgroup or not. So let us understand what this theorem says. Suppose H is a non-empty subset of a group G with binary operation star, then H is a subgroup of G if and only if A star B inverse belongs to H for any pair of elements AB belongs to H. So using this theorem we can decide whether a non-empty subset H of a group G is a subgroup or not. All we have to show is that if we take any two elements, say AB in H, then A star B inverse must be in H. So either we can use this definition to check whether given set is a subgroup or not, or we can use this one-step subgroup test. So that is as per our conveniency. Now we make one remark here. Suppose G is a group under the binary operation star, then it will always have these two subgroups. If we consider the singleton set with identity element under the same operation, then it is always a subgroup of G, and G itself is a subgroup of G. So every group must have at least two subgroups. One is set containing identity element with star and G itself under the same operation of G. So these two subgroups are known as trivial subgroups of G, and subgroups other than these two subgroups are known as non-trivial subgroups. So we consider some examples to understand the concept of subgroup. Suppose we consider the group of integers under the operation of addition, where Z is the set of integers, and we are asked to check whether the set of even integers is a subgroup of Z with addition or not. So here given group is set of integers under the operation of addition, and our set which we have to check for subgroup is set of even integers. So that we can represent by this type of elements to M, where M belongs to Z. So this is the set of even integers, and we want to check whether H is a subgroup of Z under the operation of addition or not. So either we can show by definition or we can use one-step subgroup test. Suppose we consider the definition, then first we have to show that identity of given group is also in this set H. Now if we consider Z with addition, then we know that 0 is the identity of set of integers under the operation of addition. So we can clearly write 0 as 2 into 0. So this is clear. Clearly 0 can be written as multiple of 2. So here we can say that value of M is 0, for 0 belongs to Z. So therefore 0 belongs to H. So first requirement is satisfied. Second requirement is if we take any two elements in H, then if we consider A, B in H, then we have to show that A plus B must be in H. So suppose we consider A, B in H, then we must have A equal to 2 into M1 and B equal to 2 into M2 for some integers M1 and M2. And we have to show that A plus B must be in H. Here operation star is nothing but addition, so we are considering A star B equal to A plus B. A plus B can be written as 2M1 plus 2M2, that is 2 times M1 plus M2. Now M1 and M2 are integers, so M1 plus M2 is also an integer, so that we denote by M. And here we can say that for M equal to M1 plus M2 belongs to Z. So therefore A plus B is also a multiple of 2, that is it is even integer. So therefore A plus B belongs to H. And third requirement is we have to show that inverse is also in H. For any A belongs to H, A inverse must be in H. So that we can show here. Let A belongs to H, then A equal to say 2 into M1 for some M1 belongs to Z. Now A inverse is nothing but minus A. If we recall, under the operation of addition, inverse of any integer is its negative. So A inverse equal to minus A, and here this A is 2m1, so we can write 2 into m1. This we can rewrite as 2 times minus m1, and because m1 is an integer, minus m1 is also an integer. Therefore A inverse equal to 2 times minus m1, where minus m1 belongs to Z. So that shows that A inverse is also in H. So all the three conditions are satisfied. Identity belongs to H. Here identity is 0, and if we take any two elements in H, then A plus B is also in H, and if we consider any element in H, then A inverse is also in H. So therefore H is a subgroup of Z under addition. So in this way we can show that given set is a subgroup of a given group. Now if we don't want to go by definition, we can use one-step subgroup test. So here we can use that theorem also. H is nothing but 2m, m belongs to Z. First we have to show that H is non-empty. So for that it is clear that 0 is 2 into 0, for 0 belongs to Z. So therefore 0 belongs to H. Therefore H is a non-empty subset of Z. Now for one-step subgroup test, we take two elements in H. Let AB belongs to H. Then A equal to 2 into M1 and B equal to 2 into M2, where M1 and M2 are integers. Now we have to show that A star B inverse belongs to H. Now here operation is addition and B inverse is minus B. Under the operation of addition, inverse of B is negative of B. So we have to show that A minus B is in H. So now we consider A minus B. A plus, or we can write in this way also, A star B inverse equal to, here star is addition operation, B inverse is minus B. This we can rewrite as A minus B, and this is equal to 2m1 minus 2m2, that we can rewrite as 2 times m1 minus m2, and this is nothing but 2 times m, where m equal to m1 minus m2 is also an integer. So therefore A star B inverse or A plus B inverse belongs to H. So therefore H is a subgroup of Z with addition. So in this way, either we can use one step subgroup test or we can use the definition of subgroup to show that given subset of a group G is also a subgroup or not. So this is all about this session. I hope you like it. In the next session we will discuss some more problems on subgroups. Thank you.